Okay, here we're going to go ahead and go through the multiple choice solutions on your review. Anne claims that a store-brand fertilizer works better than homemade compost as a soil enhancement when growing tomatoes. To test her theory, she plants 2 tomato plants in each of 5 planters. 1 plant in each planter is grown in soil with store-brand fertilizer, and the other plant is grown in soil with homemade compost. So then they randomly choose which plant gets which. In 3 months, she will harvest and weigh the tomatoes from each plant. What is the correct confidence interval Anne should use to analyze these data? So there's a natural pairing of measurements here because each planter is going to have the same environment like lighting and water. And the 2 plants have different treatments. We will subtract the weight of the 2 plants in each planter. All right, well, weight of the tomatoes anyways. And then we'll create an interval for the average of the differences. So if you look, see that average of differences, whereas this is the difference of averages. So the correct answer here is A. It's a paired t-interval for the mean of the differences. Now it's not Z because we're dealing with means, and we use t-intervals in the student's t-distribution when working with means. Number 2, we want to construct a 1-sample t-interval for a population mean using data from a population with unknown shape. In which of the following circumstances would it be inappropriate to construct the interval based on an SRS of size 14 from the population? So 1, let's first of all look at the conditions. And do we have a random sample? Is the population less, or the sample less than 10% of the population? And of course, the distribution. Note that it's okay if it's less than 30, and we see that it's 14. So they need to either tell us it's normally distributed, or the sample data show no strong skew or outliers. So it really has nothing to do with how big the standard deviation is. A slight skew is okay. If the stem plot of the data is roughly bell-shaped, that's approximately normal, right? But if a box plot shows the values above the median are much more variable than the values below the median, that means there's going to be some strong skew. So choice D would be the one where it would not work. Number 3, do high school seniors with part-time jobs spend less time doing homework per week on average than seniors without part-time jobs? For a random sample of 45 seniors with part-time jobs, the mean amount of homework time is 4.2 hours with a standard deviation of 3.8 hours. For a random sample of 45 seniors without part-time jobs, the mean amount of homework time is 5.8 hours with a standard deviation of 4.9 hours. Assuming the conditions are met, which of the following is the correct standard error for a 95% confidence interval for a difference in the population means? So I'm pulling this up. This is straight off your formula chart. It's on the back for means, differences in means. And we know what S1, N1, S2, and N2 are. So again, a standard deviation for the first is 3.8. Sample size is the same for both. Standard deviation for the second one is 4.9. And I look and see which of these most closely matches that, and it is choice B. Number 4, a 90% confidence interval for the mean mu of a population is computed from a random sample and is found to be 90 plus or minus 30. Which of the following could be the 95% confidence interval based on the same data? So we know that a 95% confidence interval will be wider than a 90% confidence interval. So this eliminates choices A and B. So let's go ahead and do a worst case scenario with the smallest sample size, which is 2. So degrees of freedom is 1. And we'll go ahead and find T star for both samples. All right, for both intervals, I should say. So we have for confidence level 90%, you're going to do T inverse T. T star is inverse T. Our left area is 0.90 because we're doing a 90% interval and we have the central area. And then we're going to add 0.05 because that's also to the left of the interval. So we get 0.95 in degrees of freedom. And I'll go ahead and review how to do this with a calculator. So first we'll go ahead, I'm going to do both the 90% and the 95% confidence intervals. I'm going to hit second distribution. We're doing a t distribution, so I want number 4. And actually I have it right there. So the easiest way to do this is probably to say when you're given a confidence interval, it's giving you the middle piece, and go ahead and add the left piece, and that will give you the whole left area, because the area on inverse t is not center and it's not right, it's always left area. So here we have degrees of freedom. We're assuming in this case the worst case scenario of 1 degree of freedom, that's when the curve is the widest. And you can see that our test statistic in this case is 6.313. All right. And then we'll go ahead and do another one with a 95% confidence interval. So let's go ahead and second distribution, inverse t. And instead of, we now have 95% in the center, and I want to add half of the leftover. The leftover is 0.05, and half of that is 0.025. We're still keeping the same degrees of freedom, and we calculate and we get a test statistic of 12.71. So here are our two values, 6.31 and 12.71. So margin of error for 95% should be roughly twice as large as compared to 90%. Why is that? Margin of error, if you recall, is your test statistic times your standard deviation or standard error. And our standard error should be the same for both of these. So the only thing that's really changing is the test statistic. I mean, not the test statistic, the critical value right there. And you can see it's about twice as big. So D doesn't work because it's more than twice as big. And this is the worst case scenario. We get just over twice as big, but not that big. So we cross off D, and our answer is C. Number 5. You want to compute a 90% confidence interval for the mean difference in height for mothers and their adult daughters using a random sample of 30 mothers who have an adult daughter. What critical value should you use for this interval? What's it? 90%. And our degrees of freedom is 29, because I go 30 minus 1 is 29. So we're going to use inverse t again. Our central area is 0.90, but I've got to add the piece on the left. So it's half of the leftover, 0.05. Degrees of freedom is 29. And we'll go ahead and practice this one more time with the calculator. The rest of the problems, I'm just going to write the formula. It's second distribution to get to inverse t. And then let's go ahead and clear this up. So we are doing, actually, you can probably see that I actually, well, all right. So we're doing a 90% confidence interval. So I'm going to say 0.90. But the problem is this area doesn't give me the chance for left, center, and right. And I actually want 90% in the center, which means I have 5% on the left and 5% on the right. So the area I need to put in here is the total to the left. So I'm going to take the 90 in the center plus that extra 5. And then my degrees of freedom is basically 30 minus 1. And go ahead and hit enter. And there you go. There's your critical value. So the answer is 1.699. Number 6. A Census Bureau report on the income of Americans says that with 90% confidence, the median income of all U.S. households in recent years was $57,005 with a margin of error of $742. Which of the following is the most appropriate conclusion? Well, usually, first of all, let's go ahead and pull up what confidence level means. This is straight out of your notes. So if you use a C% confidence intervals, often about C% of your intervals will capture the true parameter value. So it's not about probability or percent of households. And you can see the first one, 90% of all households had incomes of that. No, we'd have to do like a normal CDF or something to figure that out if we had all the data. We cannot be sure that the median lies in the interval. We're only confident. We're not sure. Sure is like 100% confidence. We don't, 90% of all possible samples of this same size would result in a sample median that falls within. 742 of 57,005. Well, if that were the true mean, that's probably close to true. But the problem is we don't know that that's the true mean. This is just a result for this particular interval. 90% of the households in the sample interviewed by the Census Bureau had incomes in this interval. No, that's not what the interval means. Let's go to E. The Census Bureau got the results $57,005 plus or minus $742 using a method that will capture the true median income 90% of the time when used repeatedly. That matches our definition of confidence level. A quiz question gives random samples of n equals 10 observations from each of two normally distributed populations. Tom uses a table of t distributions and 9 degrees of freedom to calculate a 95% confidence interval for the difference in the two population means. Janelle uses her calculator's two-sample t interval with 16.87 degrees of freedom to compute the 95% confidence interval. Assume that both students calculate the intervals correctly. Which of the following is true? So it looks like we're looking to see whose is wider or if there's information. We're just trying to figure out if there's information. Janelle did not make a mistake. You are allowed to have degrees of freedom be not a whole number. In fact, this is usually the better number to use. So I'm not going to dissuade you and say, oh, you must do these by hand. If you're using the calculator, report what the calculator gives you. So let's go ahead and use the degrees of freedom and our confidence level to figure out what the different critical values are. So Tom's would be 0.95 plus the 0.025 because we're trying to do a 95% confident. And again, you take half of the leftover and add it on, and that gives you the right area. Degrees of freedom is 9. That's what he used. So you have 2.26. Janelle has the same exact area, but her degrees of freedom is 16.87. And you can see that her t-star is smaller. So that gives us Tom's confidence interval is wider. Why? Well, the margin of error is just t-star times your standard error. So since Tom has a higher t-star, he is going to have a wider interval. They both have the same standard error for the test, for the statistic. Number 8, experiments on learning in animals sometimes measure how long it takes mice to find their way through a maze. The mean time is 18 seconds for one particular maze. A researcher thinks that a loud noise will cause the mice to complete the maze faster. She measures how long each of the 10 mice takes with the noise stimulus. What are the null and alternative hypotheses for the appropriate significance test? So hypotheses always use mu for mean, so cross off A, B, and E. A and B are using the statistic, and E is using a proportion, but we're doing means. The null is always equals, so that pretty much says it's going to be C. In addition, we know it's C because the researcher thinks the mice will be faster. That's why she's gathering the research. That is for the alternate hypothesis. So the correct answer is C. Number 9, a confidence interval for mu based on n equals 15 observations from a normal population is negative 0.73 to 1.92. If we use this confidence interval to test the hypothesis, h naught mu equals 0, and our alternate is that it's not 0, what is the appropriate conclusion? So because 0 is in the interval, 0 is a plausible value. We fail to reject h naught. So that eliminates choices A, B, and C. Then we just have to figure out our significance level. Well, it's 0.05. I mean, we don't technically have to figure it out because we got the same values for both choices. So the rejection zone, because it's two-sided, the alternate, well, then we are saying that that whole area outside of it is the significance level. It's 0.05. And we always fail to reject the null. We don't reject the alternate. We either fail to reject the null or we reject the null. And then we have evidence for or not so much evidence for the alternate. So the correct answer is D. Which of the following has the smallest probability? So I'll go ahead and do these by hand so you can figure them out. But there's probably a way you can intuitively figure this out. So let's go ahead and just do it. It's pretty easy to knock out. So the probability that Z is less than 2 on a normal, so that would be normal CDF, lower is negative infinity, upper is 2, mean is 0, SD is 1, we get 0.977. T is going to be the TCDF because we're using students' T distribution. In this case, we're going greater than 2, so 2 is our lower, upper is infinity, degrees of freedom is 2, 0.092. T is less than 2, and this time we have 5 degrees of freedom, we get 0.949. And T is greater than 2, it's just the complement, and we get 0.051. Finally, we have the probability that Z is greater than 2, and that gives us a probability of 0.023. So you can see if you just quickly put those in your calculator, you would get the correct answer. Another thing to think about is that T distributions are wider, so they have more area on the outside than normal distributions. Since we have the same, we'll call it test statistic, 2 in every situation, to get the tiniest area, you use the normal distribution and you go to the right of it. And that would also give you E. So technically you didn't have to calculate all these, but it was pretty straightforward. Number 11. A study of road rage asked separate random samples of 596 men and 523 women about their behavior while driving. Based on their answers, each respondent was assigned a road rage score on a scale of 0 to 20. Are the conditions for performing a 2-sample t-test satisfied? Well, let's go look at the conditions for the 2-sample t-test. And I pulled these from that little 2-page tables that I gave you from StatsMedic. So we have, these are the 3 conditions. It is a random sample, so that's fine. It's reasonable to assume there are more than 10 times 596 male and 10 times 523 female drivers. All right. It's probably true just in Round Rock. And then finally, looking at the data, both samples are larger than 30. So we have met all conditions. We have 2 independent random samples and large sample sizes. Number 12. Are TV commercials louder than their surrounding programs? To find out, researchers collected data on 50 randomly selected commercials in a given week. With the television's volume at a fixed setting, they measured the maximum loudness of each commercial and the maximum loudness in the first 30 seconds of regular programming that followed. Assuming conditions for inference are met, the most appropriate method for answering the question of interest is, well, so there's a natural pairing of data. So each television set has 2 measurements, the volume during the commercial and the volume right after the commercial. During the regular programming. So they're on the same channel at nearly the same time. So we're going to do a paired t-test for a mean difference. Number 13. A researcher wished to compare the average amount of time spent in extracurricular activities by high school students in a suburban school district with that in a school district of a large city. The researcher obtained an SRS of 60 high school students in a large suburban school district and found the mean time spent in extracurricular activities per week to be 6 hours with a standard deviation of 3 hours. The researcher also obtained an independent SRS of 40 high school students in a large city school district and found the mean time spent in extracurricular activities per week to be 5 hours with a standard deviation of 2 hours. Suppose that the researcher decides to carry out a significance test, H0, that the mean suburban time, and the mean city time were the same versus a 2-sided alternative. So 2-sided just means that the alternate is not equals to, not less than, not greater than. It could be either one. So first of all, we have our data from our samples. We have the mean, the standard deviation, and the sample size, right, for both samples. Then I'm going to pull up this formula. This is actually from your StatsMedic, the 2-page with tables and everything that I gave to you. This is also on your math chart, but it tends to say statistic minus parameter divided by standard error for the statistic. All right. So in this case, our statistic is the difference in these two. So we'd go 6 minus 5. And remember, we're hypothesizing both of these are the same, so that'll be 0. And then we put the 3 squared over 60 and the 2 squared over 40. Now you can see that we have actually these two look the same. The only difference is one has a z and one has a t. Because we're testing for means, we're using the t distribution, not the normal distribution. So the correct answer is B. Then they say the p-value for the test is 0.048. So a correct conclusion is, and you can see we got some fail to rejects and some rejects. So since 0.048 is less than 0.05, even though it's close, it's still less, we reject H0. A, B, and C are incorrect because we're not going to fail to reject, we're actually going to reject. And the reason we reject is because our evidence is convincing, which gives us choice E, that the alternate might be true. All right. Now, last one, number 15. Researchers want to evaluate the effect of a natural product on reducing blood pressure. They plan to carry out a randomized experiment to compare the mean reduction in blood pressure of a treatment natural product group and a placebo group. Then they will use the data to perform a test of the null is the differences are 0, and the alternate is the differences are greater than 0, where the mean mu of t is a true mean reduction in blood pressure when taking the natural product, and the other one is for the placebo. The researchers would like to detect whether the natural product reduces blood pressure by at least 7 points more on average than the placebo. If groups of size 50 are used in the experiment, a 2-sample t-test using alpha equals 0.01 will have a power of 80% to detect a 7-point difference in mean blood pressure reduction. If the researchers want to be able to detect a 5-point difference instead, then the power of the test would be what? Well, it's easier to detect the difference if it's 7 points than 5 points. And power is the ability to detect the difference. So if we go down to 5, the power goes down. So it would be less than 80%.